So today we're going to talk about comparing linear versus nonlinear functions. So remember, the graph of a linear function shows a constant rate of change. Remember, we referred to that constant rate of change as having a slope. So they have the same rise over run. The nonlinear function doesn't have that constant rate of change. So the points aren't the same rise over run every time. So what happens is the graph is not straight, where we know a linear function that has the constant rate of change is going to be a straight line. The nonlinears doesn't have a constant rate of change, and it's not straight. So we want to first look at tables. So looking at these tables, we want to know if they're linear or nonlinear. So I could definitely graph these, right? But again, we can just focus on slope. Change in y, change in x. If there's a steady, consistent slope throughout my table, then I know I have a linear function. So let's look at our points. So the y's are going down by 8, down by 8, and down by 8. So then my change in y is down by 8. But I need to make sure I see something consistent on the x's. Plus 3, plus 3, and plus 3. So that would mean, yes, we do have a steady slope of a negative 8/3. So what we would say is this first table is linear. Looking at the second table, so we see plus 9, plus 22, plus 55. So on first look, we would say, well, that's definitely not linear. But we can't make that decision until we've looked at the x's as well, because they also might be changing by different numbers that would give me the same slope between all those numbers. So looking at the x's, well, I see a plus 2, another plus 2, and another plus 2. So because of that, and it's really the x's that are deciding this, because the x's are changing by the same number and the y's are not, then we would say non-linear. But it is important to notice that you can't just look at the y's or just the x's. Because, for example, if it was going up by 9 on the first one and then up by 18 on the second one, and then the first one was going up by 2s and the second one was going up by 4s, it could still be a slope. But once one of them is steady and the other one isn't, then it's definitely not linear. Now, identifying functions from equations. So a function, if I can write this as y equals mx plus b, and we talked about that in a previous lesson, I can say it's linear if I can see the equation as y equals mx plus b. Well, this first one doesn't look like it, but if I do my distributive property, 4x minus 4, that is definitely linear. Looking at the second one, though, remember, we need to have the slope right up here next to my x. Well, notice the x is really kind of up in the numerators. This x down here isn't a denominator. There's no way I can write this in slope-intercept form. So this is definitely one that we're going to have to say non-linear. And so what I'm going to add to this too, so the variables can't be in the denominator. I'm going to write no variables in denominator. That's number one. And then number two, the other one we want to look for is no exponents. On variables. Those two things I would end up having non-linear. So it's important. Oh, I didn't even spell that right. I'm going to erase that. So exponents is not spelled the way I spelled it, so hopefully you caught that and spelled it correctly. There we go. So you can't have exponents on my variables, and in the case like example B, we can't have variables in the denominator. Those would be definitely non-linear functions. The next one is interesting. So the next one we can tell by a graph. If it's a perfect straight line, then we can say that it is linear. So very quickly, this first one is non-linear. It is definitely not showing a constant rate of change or slope or a straight line. The second one is definitely linear. Now, we talked about how the function definition says non-verticals. Don't confuse that with this one, which is horizontal. Horizontal is fine. We can't have the vertical line to be a linear function, but a horizontal line is fine, and any diagonal straight line is fine. They are all linear functions. So on this one, we have two different accounts earning money. We have account A and account B. So what we first want to do is graph the data and compare the balances over time. So I'm first just going to say, again, we aren't going to have negative time. You could have negative balances, but we're just going to kind of focus on positive. Remember, this would be the y, this would be my x. So the time would be years down here, and the balance would be how much money is in the account would be on my y value. So this one's going to be a little bit of estimating things. We're not going to get it nice and perfectly done, but I'm going to do my years as in half years, just because we're only going up to 5, and I would like to stretch this as much as I can. The second part, what I am going to look at doing too, is I'm going to do one of these little breaks. And we're going to jump right up to 100. And then from there, I am going to go up by 5s, which we're going to have to do a little bit of adjusting here at the top, because I'm going to run out of space like we did on the previous graph. So this is not ideal. We're going to have to kind of go with the idea that there's your 160 that we need to kind of get to. Not ideal. Obviously, if you have a real graph paper, you would want to do it a little bit better to see that the grids match up. So then I'm going to do account A in blue, and then we'll do account B in a different color. So looking at my year and the balance, so in the blue, at 0 years I have 100. At year 1 I'm at 110. Year 2, 120. Year 3, 130. Year 4, 140. Year 5, 150. So if I kind of connect that, we see a nice, perfect straight line. Then when I look at the second one, account balances for B, we'll do that one in green. So the B also starts at 0, 100. Also 110 at year 1. Then we get a little bit of a difference. So we're at 121. Then we're at 133. Then we're at 146. Then we're at 161. So notice this is not a straight line. This is going to have a little bit of a curve to that. Okay, so account B is actually earning us a little bit more money as it goes. This goes back to simple interest versus compound interest, which we're not really studying this year, but that's why this is happening. So the interest on the B is compounding, so it's climbing a little bit faster. So then it says to compare the balances over time. So we're just going to simply kind of write this as A has a linear graph while B is nonlinear and B is earning more as time goes by. So you can see that this green line is pulling away from the blue line. It would continue to do that if we went to year 6, 7, 8, 10, 20. It would continually be higher than account A. So here's the last thing I want you to do. I want you to look at each of these four, and we'll talk about whether they're linear or nonlinear. So what I would suggest you do is that you pause the video. I will just go through these, but if you pause the video and try it, and then come back in to see how you did, it'll give you a chance to see if you understand how this works. So the first one. Linear means I can find a steady slope. So if I look at my y's, we're going down by 5s. And at the same time, we're going up by 7s. So that would definitely mean this is linear because I can determine a single slope for the entire table. Looking at B. Well, B, we see a straight line. Until we hit here, we see another straight line. But as an overall graph, this is not a straight line. So as an overall graph, this is nonlinear. It definitely has some portions that look linear, but as an overall graph, we have to say it's nonlinear. This next one is tricky because we talked about this exponents in the denominator, and it doesn't look like y equals mx plus b. But really, it has to be written as y equals mx plus b. In reality, this is the same thing as 4/3 times x, that's where the 4x over 3 comes in, plus 0. It's just that when we go one step further, instead of writing 4/3 x, we just did the 4x over 3, and we dropped 0. So this one is definitely linear. Okay, the slope would be 4/3, the y-intercept is at 0. And on the last one, if you remembered what I said, the nonlinears have exponents on our variable and would have the x's or the variables in denominators. So because of that, this is definitely non-linear. And you'll learn more about what this type of a graph looks like next year when you're in algebra. So hopefully it makes some sense with these comparing linears versus nonlinear. Remember, the word line is in linear, which means a straight line is linear. It also means that we have the same slope through all of our points, the same rise over run. If you have any kind of questions, please feel free to ask me when I see you in class.